Hello, welcome to another lecture in the course on 3G, 4G wireless communication systems. In the last lecture, we had started our discussion on the Alamuti code, which we said is a space-time block code designed for 1x2 MIMO systems, that is for one receive antenna, two transmit antennas. Subsequently, we had derived the SNR at the receiver for the Alamuti code. We said it yields second order diversity because there is a norm h square, and in fact it yields second order diversity without knowledge of the channel at the transmitter. So, that is the biggest advantage of the Alamuti code. Further, we said it also results in a 3 dB loss in SNR compared to the scenario where the channel is exactly known at the transmitter. So, it yields a full diversity order, however, there is a 3 dB loss in terms of SNR. That is the price we said that has to be paid because of lack of the channel information at the transmitter. And we also said Alamuti belongs to a unique class of space-time codes, block codes known as orthogonal space-time block codes, alright, because orthogonal because the different columns are orthogonal, which makes detection easier. It is a code which spans both space and time, and it is a block code because it involves a block of symbols. Hence, it is belongs to a class of codes known as orthogonal space time block codes or OSTBC. And in this context, we had also seen an example of an Alamuti system in action, that is a 1x2 system employing the Alamuti code. We had also seen another example of an orthogonal space-time block code for a 1x3 MIMO system, that is, that has one receive antenna, 3 transmit antennas, and there was a code which transmitted 4 symbols in 8 time instance. Hence, we said this is a rate half code. Alright, so we had seen a rate half code, orthogonal space-time block code for a 1x3 MIMO system. And finally, we also started our discussion on nonlinear MIMO receivers with VBLAST, which is the Bell Labs vertical, Bell Labs layered space-time architecture for MIMO reception. This is the point at which we left last time. So, let us continue our discussion from this point, that is, we were talking about nonlinear MIMO receivers. So, let us begin the discussion on nonlinear MIMO receivers, and we said VBLAST is an example of nonlinear MIMO receiver. VBLAST, where V stands for vertical, Bell Labs layered space-time architecture. We also said that this employs a unique method of reception known as successive interference cancellation. It employs successive interference cancellation. Hence, this is also abbreviated as SIC, where essentially the impact of each estimated symbol is cancelled from the received symbol. So, what this means is impact what this means is, unlike previously, which was a one shot detection for all the symbols in a 04 SING or MMSC receiver, here you estimate a symbol, cancel its impact, estimate another symbol, cancel impact. That is why you successively cancel the interference from the estimated symbols. Hence, this is known as successive interference cancellation. Further, it is non-linear in nature. Further, because it employs SIC, it is non-linear in nature. alright, because it employs successive interference cancellation. This receiver is non-linear in nature, alright. We are going to look at how in detail how this receiver works, alright. So let me go back to my MIMO system model, where we have y bar equals H matrix plus n. This is an R cross T channel matrix, and we are also assuming R greater than or equal to T. Remember, R is greater than the number of rows, or the number of receive antennas is greater than or equal to the number of transmit antennas. Now what I am going to further write this as, I am going to write this as, I am going to illustrate it, its column structure H1 bar, H2 bar, HT bar into X1, X2, X T plus n bar, where these are the T columns. Remember, we are considering an R cross T MIMO channel matrix, so it has T columns. I am denoting them by H1 bar, H2 bar, so on up to HT bar. In fact, these are the T columns of the matrix, and these are the T symbols, that is X1, X2, XT are the T symbols. Hence, this can also be written as, simply expanding it out, y bar equals H1 bar X1 plus H2 bar X2 plus HT bar XT plus n bar. What I am doing is I am simply expanding this out as a in terms of its column. So I can write it as H1 bar X1 plus H2 bar X2 plus until HT bar XT, where each H1, H2 up to HT bar is the column of this MIMO channel matrix, alright. So now what I want to do is I want to consider the pseudo inverse, consider the pseudo inverse or the left inverse of H, alright. Let that matrix be given by Q. So Q equals H pseudo inverse, that is what we are considering. We are considering the matrix Q, which is the pseudo inverse of the matrix H, which we had already looked in terms of the earlier, we had already looked at that in terms of the zero forcing receiver. Remember, we said left inverse of H times H is identity, that is what we had used for zero forcing reception. We are still going to use that, however, it is not exactly the same as the zero forcing receiver, as you are going to see shortly. Now by definition, let this matrix Q equals, I am going to write this matrix Q in terms of its rows, just for notational convenience. It has T rows because H has T columns. The pseudo inverse of H, that is Q, has T rows, alright. So Q times H is nothing but a T cross T identity matrix, alright. It's a T cross T identity matrix, okay. So what I am going to write this as is, so we know that Q times H equals identity, that is what we know, implies Q1 Hermitian, Q2 Hermitian, QT Hermitian times H1, H2, HT equals identity. In fact, this is the identity of dimension T, alright. I will write this as, I will expand out the matrix product and I will write this as nothing but Q1 Hermitian H1 bar Q1 Hermitian H2 bar, Q2 Hermitian H1 bar, Q2 Hermitian H2 bar, and so on. And this matrix, as we know, is equal to the T cross T identity matrix. Okay. So, Q Hermitian H, I have expanded it in terms of the rows of Q, that is Q times H, I have expanded it in terms of the rows of Q and columns of H. What I am saying is that has a structure that looks like this, which is equal to the identity matrix, which essentially means that we have the following, that is Q1 Hermitian H1 equals Q2 bar Hermitian H2 bar, so on and so forth, equals 1. However, the off diagonal elements in this matrix are 0, which means Q1 bar Hermitian H2 equals Q2 bar Hermitian H1, so on and so forth, and all those off diagonal elements are 0. Alright, hence we can essentially summarize this as, this can essentially be summarized as, let us consider the product Qi bar Hermitian H j, this is equal to 1 if I equals j, and this is equal to 0 if I is not equal to j. That is, the rows of Q are such that Qi bar Hermitian H j bar equals 1 if I equals j, that is Qi bar Hermitian H I equals 1, but Qi bar Hermitian H j equals 0 if I is distinct from j or I is not equal to j. Right? And we can use this, I mean we knew this earlier, because Q times Q is the left inverse of H. We had already seen this case in the case of MIMO 0 forcing. However, we are now exploring this property in depth. So, now I can use this advantageously for the detection or for a detection scheme. In fact, you can observe that Q1 Hermitian is orthogonal to H1, is orthogonal to H2, H3 up to Ht. So, I can use this to cancel the interference from X1, X2, X3 up to Xt. So, let me illustrate this point. So, I have Y1, let me write this as, or I have Y equals H1 bar X1 plus H2 bar X2 plus Ht bar Xt plus some noise. What I am going to do now is I am going to left multiply Y bar by Q1 Hermitian and cancel the interference from H2, H3 until Ht. I will do this as follows. So, what I am going to do is I am going to left multiply, I am going to form Y1 tilde equals Q1 bar Hermitian Y bar, that is I am going to multiply by Q1 bar Hermitian Y bar, I am going to left multiply by Q1 bar Hermitian Y bar, which is essentially can be represented as Y1 tilde equals Q1 bar Hermitian into H1 bar X1 plus H2 bar X2 plus Ht bar Xt plus Q1 bar Hermitian N bar. This is some noise N tilde, and at this point I can see that Q1 bar Hermitian H1 is 1, hence this is 1 times X1. So, Y1 tilde equals X1 plus Q1 bar Hermitian H2 is 0. So, 0 plus so on plus 0 plus some n tilde. So, now what I have done essentially is I have used the properties of the zero forcing receiver, left multiplied by q1 bar Hermitian, which is orthogonal to h2, h3 until ht, and I have cancelled the interference from those streams. Now, what I am going to do is, now if you look at this, from this y1 tilde equals x1 plus n tilde, I can employ this to decode x1. So, this can now be employed So, employing y1 tilde, I can decode x1, that is the stream transmitted from transmit antenna 1. Okay. Now, what is done is actually something interesting. What happens now is something different from what happens in 04. Now, I will remove the effect of having decoded x1. I can remove the effect of x1 from the received vector y. Alright. So, now what I am going to do is I am going to take y bar and remove the effect of x1, alright, where x1 is estimated by cancelling out the interference from the other streams, which is essentially h1 bar x1 plus h2 bar x2 plus ht bar xt plus n bar, all right, minus h1 bar x1. Of course, this is assuming that the detection process is accurate, so that I am able to decode the symbol x1 accurately. Now, if the decoding is not accurate, then we will have problems in this, in the sense those errors will propagate. However, for simplicity now, I am assuming that we are able to accurately detect x1. In that scenario, what happens is the h1 bar x1 end up cancel, because we are subtracting the interference. What I have is, I will denote this as y2 hat and y2 hat equals h2 x2 plus h3 bar x3 plus ht bar xt plus n bar, which can be equivalently represented as y2 hat equals h2 h3 ht x2 x3 xt plus n bar. Hence, now look at this, this is effectively, this has t columns, this has t minus 1 column. So, hence this is an R cross t minus 1 matrix. Hence, we have effectively reduced, by cancelling the interference from x1, by cancelling x1, we have effectively reduced this to an R cross t minus 1 MIMO system. We have effectively reduced this to an R cross t minus 1 MIMO system. I will denote this as, I will denote this matrix as H1. So, we now have y2 hat equals H1 times x2 up to xt plus n bar. I will now consider a matrix Q1, which is the pseudo inverse of this H1. Consider Q1 equals H1 pseudo inverse. Now we consider we have a different effective MIMO channel, one which is R cross T minus 1 dimensional. I will consider the pseudo inverse of this matrix, consider the row Q2 Hermitian in this matrix Q1, and then I will cancel the interference from all the rest of the vectors, decode X1 and repeat the process. So now I will repeat the process. So now repeat the process by decoding X2 and so on. All right. So what happens now is essentially you consider cancelling the interference of H3 to HT by considering the appropriate row in this matrix Q1, decode X2, cancel X2, again repeat the same procedure for X3 and so on, and this procedure continues. Hence it is known as successive interference cancellation, because you are successively cancelling the interference by detecting the symbols. All right. So this is known as successive interference cancellation, because you are successively removing the interference. Now what is the advantage of this scheme compared to the other detection scheme? As you decode progressively, as you progress with this scheme, the diversity order of the system improves. So the advantage of this scheme is the symbols that are detected at later stages in this procedure experience higher diversity order. So advantage is diversity order progressively increases progressively increases through the procedure, progressively increases as you proceed For instance, consider a simple example. Once you have decoded x1, x2 up to xt minus 1, what is left in the last stage is y hat of t equals ht of xt plus nt. That is, you have decoded x1, x2 up to xt minus 1, cancelled the interference from them. What is left is simply y hat t is ht times xt, and remember this is now effectively an R cross 1 channel, which is simply receive diversity, that is like equivalent to having R receive antennas, 1 transmit antenna, we use rth order diversity. So this yields rth order diversity, which is much higher than what you can normally experience if you do simply MIMO 046. So the later streams, the streams that are decoded later, experience progressively higher diversity. So let me also summarize this. That are decoded later experience progressively higher diversity, meaning progressively higher accuracy of detection and progressively lower bit error rate. Alright, so that is how the diversity order increases. This is a non-linear scheme. As you can see, it is not linear. You decode a symbol, which is a non-linear operation, you remove the effect of its interference, decode the next symbol. So this is essentially a non-linear receiver. Alright, so let me illustrate this with the help of an example. So let me give you a concrete example to illustrate how this V-blast receiver works. So let's proceed to the example. I am going to consider again a 2 cross 2 MIMO system. Y bar equals 1 1 2 3 x1 x2 plus n bar. So, I am considering a 2 cross 2 MIMO system. So, this is a 2 cross 2, this is a 2 cross 2 MIMO system. Alright, I am transmitting two symbols x1 x2, receiving a vector y which is 2 cross 1 dimensional. Noise bar vector is also 2 cross 1 dimensional. You should be very familiar with this system model at this point. So, the channel matrix H is nothing but 1 comma 1 2 comma 3. The pseudo inverse of this matrix, left inverse, is given as, in fact, which you can see, the left inverse of this matrix is nothing but 3 comma minus 2 minus 1 comma 1. You can in fact check this by multiplying 3 minus 1 minus 2 1 into 1 1 2 3 equals nothing but 3 times 1 minus 2 times 1, this is 1, 6 minus 6, this is 0, minus 1 plus 1, this is 0, 3 minus 2 plus 3, this is 1, this is identity. Hence, this is in fact the left interference. This is the pseudo inverse. And now, if we look at this pseudo inverse, we have 3 comma minus 2 minus 1 1, this is our matrix Q. In fact, the rows are nothing but 3 comma minus 2 is the row Q1 Hermitian, minus 1 comma minus 1 is the row Q2 Hermitian in this matrix, which means this Q1 Hermitian is orthogonal to H2, Q2 Hermitian is orthogonal to H1. So, now what I am going to do is I am going to use Q1 Hermitian multiplied by Q1 Hermitian to cancel the interference being caused by X2, and this can be represented as follows. This is 3 comma minus 2 into, I am going to multiply it by y bar, which is 1 comma 1 2 comma 3 x1 x2 plus Q1 Hermitian n bar. We said we are going to denote this by n1 tilde. And now you can observe that 3 comma minus 2 into this column 1 comma 1 yields me a 1, 3 comma minus 2 into the column 2 3 yields me 0 because of the orthogonality, and this is x1 x2 plus some n1 tilde, which is essentially nothing but 1 comma 0 into x1 x2, this is x1 plus n1 tilde. Hence, what I have reduced this to is, I have reduced this to, let me use the notation that I have been using before, which is y1 tilde x1 plus n1 tilde. Now, I can detect x1 from y1 tilde, detect x1. As you can see, the interference from x2 x3 so on, that has been removed. All right. So, now the interference from x2 has been removed, which is the only other symbol. All right. So, now I can detect x1, and what I will do is, now I will multiply x1 by h1 and cancel its impact on the received vector y. Now, what I will perform is, I will perform y2 hat equals y bar minus h1 x1, which is essentially 1 comma 1 2 comma 3 x1 x2 minus h1 1 comma 1 into x1. Of course, the noise remains as it is. This is nothing but, you can see, now reduces to 2 comma 3 x2 plus n bar if the decoding is exact. Let me write this again here. Y2 bar, Y2 hat equals 2, 3 x2 plus n bar. Now I can decode x2. In this case it is simple because there is no interference from other symbols. This is the last symbol in this. So I can simply use a maximum ratio combiner. So now you can use, in fact, one can employ MRC as this is the last symbol. There is no other symbol after x2, so there is no interference, which means this is the last symbol. I can employ MRC. But the more important thing you can see is this has a diversity order of 2. So this experiences a diversity order of 2. Alright, so as the diversity order progressively, because the first symbol experiences only a diversity order of 1, because diversity order is r minus t plus 1, r equals t equals 2, diversity order is r minus t plus 1, which is 2 minus 2 plus 1, which is 1. However, the second symbol, because you have removed the interference from the first symbol, that experiences a diversity order 2. Hence, the diversity order of the successively decoded symbols is better, and in fact, the diversity order progressively increases as you proceed through the stages in the V-blast receiver. Alright, and that is the principle of successive interference cancellation. Alright, so that concludes this example, and that concludes this section on the successive interference cancellation part of the V-blast receiver, which is the vertical Bell Labs layered space-time architecture for MIMO system. We want to look at one other topic in MIMO system, which is related to MIMO beamforming. Now, beamforming in conventional antenna systems traditionally refers to a technique where you have an antenna array and you are steering a beam in a certain direction. For instance, I have an antenna array. This is an array of antennas. And what I am doing is I am steering the beam in a certain direction. So, this is known as the beam. I am steering this beam in a certain direction. So, this is the beam. I am receiving signals along this direction. I am steering the beam in this direction. However, along this direction, that is, so this is maximum gain direction. This is again maximum gain. These are the null directions. Alright, this is used in a conventional sense of directional reception and directional transmission using antenna arrays. In the context of MIMO, it is slightly different because there is no sense of physical direction associated with beamforming, but there is a concept of beamforming. What that means, we are going to look at shortly. For instance, I am going to consider beamforming in the context of MIMO. In context of MIMO essentially implies transmit in one spatial direction. It essentially implies transmission in one, not even spatial dimension. That is, you transmit along a certain abstract direction in this n-dimensional space. We are going to illustrate how. Okay, so for instance, I have y bar equals h x bar plus n bar, that is the MIMO system. I am going to consider the SVD of this. Remember, we have looked at the singular value decomposition of this. I am going to write this as U sigma V Hermitian, that is the matrix H, can be written in terms of its singular value decomposition as U sigma V Hermitian. We have already seen this. V is the unitary matrix, U Hermitian, U is identity, sigma is the matrix of singular values, because this is because this structure is because R is greater than or equal to T, alright. And in fact, we have shown we can also slightly expand upon this to look at the columns and rows. I am going to look at the columns, which are U1, U2, UT, and write this in terms of the singular values sigma 1, sigma 2, sigma t. Remember, this is a diagonal matrix into V1 Hermitian, V2 Hermitian, Vt Hermitian, x plus n bar, alright. That is the kind of MIMO system I am looking at. I am just doing nothing new. I am just writing this singular value decomposition in terms of columns of matrix U, rows of matrix V, and so on, alright. So, this can be employed to illustrate beamforming in the context of MIMO. Okay, so what I am going to do now is I am going to use one of the dimensions of this MIMO or one of the modes of this MIMO channels for transmission as follows. I am going to form my transmit vector x bar as x bar equals V1 bar x1 tilde, alright. So, my transmit vector x bar, even though it is a vector, it has only one symbol, that is I am only transmitting one symbol x1 tilde. In fact, I am selecting the dominant transmission port. Remember, V1 bar is associated with singular value sigma 1, hence this is the dominant transmission mode of the MIMO channel, because associated with singular value sigma. So, even though I have T transmit antennas, what I am doing is I am only transmitting one symbol, however, I am transmitting it along V1 bar. So, this has a sense of direction, although this is not a sense of direction in normal 3-dimensional space that we are used to as in the when we mean direction. This has a sense of direction in n-dimensional space. V1 bar is essentially a unit vector in a particular direction, that is the direction in which this transmission is being done, alright. So, we are transmitting in a certain direction in n-dimensional space, alright. So, V1 bar is the now abstract, it is the abstract direction in n-dimensional space along which x is being transmitted. Okay. So, what that means is I am taking a symbol x1 tilde, aligning it with direction V1 bar, and I am transmitting it across the antennas. Now, what is the result of this scheme of transmission? I have y bar equals U1, U2, these are all columns, UT bar, sigma 1, sigma 2 up to sigma t, V1 Hermitian, V2 Hermitian, Vt Hermitian into V1, because x, remember, is now V1 x1 tilde, plus of course I have my noise vector, that is n bar. So, I am transmitting x V1 times x1 tilde as the vector x. Now, you can see this is V1 Hermitian V1 is 1, but V2 Hermitian V1 is 0, V3 Hermitian V1 is 0, so on and so forth. Vt Hermitian V1 is 0. We said V Hermitian V is identity because V is a unitary matrix, which means the columns are, which means the rows and columns are orthogonal, alright, in fact orthonormal. So, now I can write this as U1, U2, ut into sigma 1 sigma 2 sigma t into, now this vector is v1 Hermitian v1 which is 1, v2 Hermitian v1 which is 0, so on, zeros plus x1 tilde plus n bar. Now you can see this vector of 1 0 0 times this diagonal matrix sigma 1 sigma 2 up to the sigma t simply picks this diagonal value sigma 1, hence this can be represented as u1 u2 ut sigma 1 0 x tilde 1 plus n bar, and that is nothing but the sigma 1 and rest are 0, now simply picks u1 bar, and that is simply sigma 1 u1 bar x1 tilde plus n bar. In fact, this can be written as, since x1 tilde is a scalar, this can be written as sigma 1 x1 tilde into u1 bar plus n bar. Alright. So, this is now the scalar, and at the receiver u1 bar, not u1 tilde, u1 bar is the direction along which you are receiving. So, at the transmitter you are transmitting along this direction in abstract n dimensional space which is v1 bar, and corresponding to that you are receiving along the direction u1 bar at the receiver, which is the dominant receive direction. This is the dominant receive direction. Look at this, the gain associated with this, gain of equals sigma 1. So, the channel has a gain sigma 1, which is essentially because you are transmitting along the dominating mode or the greatest or the most powerful mode of this MIMO wireless communication system. Now, you can see what needs to be done. This is like a single input multiple output system. I can perform receive beamforming using the maximal ratio combiner. In fact, the maximal ratio combiner is u1 itself, because norm u1 is 1. Hence, what I do at the receiver is something simple, is I perform maximal ratio combining. So, I have y a bar equals sigma 1 u1 bar x1 tilde plus n bar. Use u1 bar can be employed for maximal ratio combining. Alright, in fact, u1 bar Hermitian y bar equals u1 bar Hermitian sigma 1 u1 bar x1 tilde plus n bar, which is u1 bar Hermitian u1 is 1. So, this is nothing but sigma 1 x1 tilde plus u1 bar Hermitian n bar, which is nothing but some n1 tilde, which is the noise. So, as a result, I have y1 tilde, this y1 tilde equals sigma 1 x1 tilde plus some noise n1 tilde. Alright, this is what I have, and the SNR associated with SNR equals sigma 1 square p, where the p is the power in the transmitter symbol divided by sigma n square, where sigma n square is the noise power. In fact, you can see sigma 1 square, this is the largest singular value, sigma 1 is the largest singular value. Alright, so you are transmitting, so your gain is the largest gain that is possible along these parallel channels in the MIMO system. So, it is the gain associated with the dominant mode, it is also the gain associated it is also the gain associated with the dominant mode. So, by transmitting this x1 tilde along this direction V1 bar, what I am able to do is I am able to effectively convert it, and of course, by doing receive beamforming, by beamforming along U1 bar at the receiver, I am able to use the dominant mode at the receiver, which means now this effectively becomes a SISO channel with gain sigma 1 and symbol transmitted x1. What the advantage of this scheme is that it results in a simplistic transmission. Alright, first of all, I want to introduce some nomenclature. Look at this. This introduces a gain sigma 1 square, which is the maximal gain possible in the MIMO channel for a stream. Hence, this is known as maximal ratio transmission. This of MIMO forming is termed as maximal ratio transmission, that is MRT. This scheme of transmitting along the dominant mode to obtain the single gain corresponding to the largest singular value sigma 1 is termed as maximal ratio transmission MRT. Alright, we had seen maximal ratio combining MRC before. This is maximal ratio transmission MRT, and the advantage of this is it results in simplistic transmission. What is the advantage of MRT? Advantage of MRT is it results in a simplistic transmission and reception scheme for MIMO systems by effectively converting. So, because you are only transmitting one symbol, there is no interference from other symbols, hence it results in simplistic transmission, also simplistic reception, because the receiver is simply a maximal ratio combiner in the dominant mode along the dominant mode of the receiver, which is U1 bar, and it is simplistic compared to schemes such as simplistic. This is simplistic compared to schemes such as MIMO, zero forcing, in fact MIMO, MMSC, all of these involve essentially computing matrix inverses, right? And also MIMO, in fact MIMO V-blast also, V-blast in fact involves computing the pseudo inverses several times. In fact, it is also simpler to MIMO V-blast and so on, right? So, this results in a fairly simplistic transmission scheme compared to the conventional MIMO receiver, but the advantage of those schemes is they have high computational complexity, but they can be used for spatial multiplexing, that is transmitting multiple information streams in parallel, hence, and higher throughput. So, it is a complexity versus throughput trade-off. And I am going to illustrate two additional properties, or I am going to mention two additional properties of my MRT, which I am not going to prove here. One, MRT is capacity optimal at low SNR, that is at low transmit power. This MRT, even though it is using only one dimension, is capacity optimal. That is kind of intuitive to see, because at low power you are using only few dominant modes. In fact, if the power is very low, you will use only one of the dominant modes, and that dominant mode is the mode corresponding to singular one. As you can see in the water filling scheme, when we have water filling, if the power is very low, then it only uses one of the modes. So, that is the dominant mode, hence it is capacity optimal at low SNR. This maximal ratio transmission is capacity optimal at low SNR. The other property is slightly difficult to see, and I will not prove it here. MRT achieves the complete diversity order which is in fact for this MIMO R cross T MIMO system, it is R times T. If I have R receive antennas, T transmit antennas, I have RT independent fading coefficients, hence the complete diversity order is R times T, and MRT achieves the complete diversity order of RT. So, this is a simplistic transmission scheme, but very reliable and yields very low bit error rate because it has full diversity, all right, which is essentially RT. So, this simplistic transmission scheme has two advantages. At low SNR, it is capacity optimal. First, it is a simplistic scheme, so it has low computational complexity. 2, it is capacity optimal at low SNR, and 3, it achieves the complete diversity order of the MIMO system. Hence, this maximum ratio transmission, which is sort of abstract beam forming in a MIMO system, is advantageous. All right. So, with that we come to the conclusion of this section on MIMO. Let me briefly again outline what are the different components that we have covered in this MIMO section. So, let me make a list of topics covered. In this MIMO section, the first we have looked at the MIMO architecture. We have started with what is a basic MIMO system. We looked at the architecture of MIMO system, which is multiple antennas at transmitter and receiver, and we developed a system model for this, which is based on the MIMO matrix channel. Then we started looking at MIMO receivers. We looked at MIMO. In fact, we started looking at MIMO receivers. We looked at the linear receivers. In fact, first we looked at linear . We first looked at MIMO linear receivers. They are MIMO ZF, that is zero forcing, and MIMO MMSC. Which is minimum mean squared error. And so, we looked at MIMO architecture model, started with MIMO architecture model, and we started looking at MIMO receivers. So, due to lack of time, I am going to close this lecture at this point. We are going to finish this in the next lecture and start with our next topic in this course on 3G 4G wireless communication systems. All right. Thank you very much for your attention.